Swirling polar vortices on the Sun represent a fascinating and complex phenomenon, likely rooted in the dynamic interplay of solar physics. These vortices, if confirmed, would be akin to giant hurricanes at the Sun's poles, driven by intense magnetic fields, plasma dynamics, and extreme temperatures. The Sun's polar regions have remained relatively underexplored, compared to its equatorial zones, but advancements in solar observation technology have provided tantalizing clues about unique phenomena occurring there. Observations suggest that the polar vortices are a result of complex interactions between magnetic field lines and turbulent plasma flows. These structures could be shaped by the Sun's differential rotation, where the equatorial regions rotate faster than the poles, causing twisting and shearing of magnetic fields. Theoretical models propose that polar vortices could form when magnetic field lines, stretching from the Sun's interior to its corona, interact with fast-moving solar winds. The Sun's magnetic field is not uniform. It is in a constant state of flux due to the solar dynamo process, which generates and regenerates these fields over the 11-year solar cycle. The twisting of these field lines near the poles may create vortical patterns in the plasma. Such vortices could have profound implications for our understanding of the Sun's magnetic field dynamics. These swirling structures might act as conduits for transporting energy and particles from the Sun's interior to its outer layers. This energy transfer could influence phenomena like solar flares and coronal mass ejections, which, in turn, impact space weather and Earth's magnetosphere. Evidence of these vortices comes from spacecraft like the Solar Orbiter and Parker Solar Probe, which are equipped to observe the Sun's poles from unique vantage points. High-resolution imaging and spectroscopic data reveal patterns of plasma motion that resemble vortex-like formations. However, the extreme temperatures and densities of the solar plasma make direct observation and interpretation challenging, requiring sophisticated computational models and simulations. The polar regions of the Sun also play a crucial role in the heliosphere, the bubble of solar wind that envelops our solar system. Swirling polar vortices could influence the distribution of charged particles within the heliosphere, affecting interplanetary magnetic fields and cosmic ray propagation. This has implications for both space exploration and our understanding of cosmic radiation. Studying these vortices also opens new doors in understanding fundamental plasma physics. The Sun acts as a natural laboratory where conditions of high energy and density mimic those found in other astrophysical objects. Insights gained from the study of polar vortices could help explain similar structures in distant stars and even galaxies. Another intriguing aspect is the potential link between polar vortices and the Sun's magnetic polarity reversals. Every 11 years, the Sun's magnetic field flips, with the north and south poles switching places. Polar vortices may act as stabilizing or destabilizing agents during this process, influencing the timing and intensity of the reversal. The formation of these vortices is likely tied to alpha waves, oscillations within the Sun's magnetic field and plasma. These waves can transfer energy across different layers of the Sun, potentially triggering and sustaining vortical motion. Understanding the mechanisms behind these waves provides further clues about how polar vortices might form and persist. Finally, the study of swirling polar vortices on the Sun exemplifies the synergy between observational astronomy, computational modeling, and theoretical physics. It underscores the importance of continued investment in solar research, not only to unravel the mysteries of our closest star, but also to protect and prepare our planet from its potentially hazardous effects. The investigation into swirling polar vortices on the Sun is far from complete, and the continuation of this research promises to deepen our understanding of both our star and universal processes. One significant avenue of exploration involves further refining the models of energy transfer within the Sun's atmosphere. The potential role of polar vortices as mechanisms for redistributing energy between the Sun's core, surface, and corona could reshape existing theories about solar energy dynamics. By studying the vortices in greater detail, scientists may uncover new pathways of energy dissipation that have remained elusive in other areas of solar research. Moreover, the interaction between polar vortices and the Sun's corona, the outermost layer of the solar atmosphere, is of paramount interest. The corona, with its unexpectedly high temperatures, reaching millions of degrees Kelvin, is a long-standing mystery in astrophysics. Polar vortices might contribute to this heating phenomenon by channeling energy upward in concentrated streams. Such processes could offer a missing piece in the puzzle of coronal heating, an area of study that has baffled scientists for decades. One fascinating aspect under investigation is whether the vortices could generate localized weather patterns in the Sun's atmosphere. Analogous to cyclones and anticyclones on Earth, these solar weather systems could create transient hotspots, density waves, and regions of enhanced magnetic activity. The existence of such features would have implications not only for understanding solar dynamics but also for predicting solar events that affect Earth. The potential role of swirling polar vortices in driving the solar wind is another frontier. The solar wind, a constant stream of charged particles emitted by the Sun, plays a critical role in shaping the space environment of the entire solar system. Polar vortices could serve as accelerators, expelling particles into interplanetary space at higher speeds and energies than previously thought. Understanding this connection could enhance our ability to forecast space weather, which is crucial for protecting satellites, astronauts, and ground-based technologies. The study of these vortices also intersects with magnetic reconnection, a process where magnetic field lines break and reconnect, releasing vast amounts of energy. Polar vortices could act as sites for frequent or intensified reconnection events, fueling solar phenomena such as jets, prominences, and eruptions. Such a connection would tie these vortices to some of the most dramatic and energetic events observed in solar physics. Additionally, polar vortices could influence the Sun's polar plumes, long jets of plasma extending outward from the poles. These plumes are thought to contribute to the fast solar wind, but their formation and variability remain poorly understood. Vortices at the poles might regulate the structure and dynamics of these plumes, offering a new perspective on their behavior. Exploring the life cycle of polar vortices is another critical focus. How these structures form, evolve, and dissipate over time could reveal much about the stability and variability of the Sun's polar regions. For instance, researchers are keen to determine whether vortices are transient phenomena tied to specific solar cycles or more permanent features that persist across multiple cycles. The implications of polar vortices extend beyond the Sun itself, providing insights into other stellar systems. Stars with different sizes, compositions, and magnetic field configurations might also host polar vortices, albeit with unique characteristics. Comparative studies could reveal whether swirling polar vortices are a universal feature of stellar dynamics or a peculiar attribute of our Sun. Technological advancements are essential to push the boundaries of this research. Future missions equipped with more sophisticated instrumentation, such as next-generation coronagraphs and magnetographs, could offer unprecedented views of the Sun's poles. Ground-based observatories equipped with adaptive optics and spectroscopic capabilities will also play a crucial role in supplementing space-based data. Ultimately, the study of swirling polar vortices on the Sun is a testament to humanity's enduring quest to understand the cosmos. By unraveling these enigmatic phenomena, we not only gain a clearer picture of our own star's inner workings but also lay the groundwork for answering fundamental questions about the behavior of stars and plasma throughout the universe. This pursuit highlights the interconnectedness of scientific disciplines, blending astronomy, physics, and computational modeling to shed light on one of nature's most mesmerizing displays. The ongoing exploration of swirling polar vortices on the Sun opens doors to understanding their potential role in the larger cosmic ecosystem. These structures, though localized to the Sun, could provide insights into plasma behaviors across a wide array of astrophysical environments, from accretion disks around black holes to the turbulent atmospheres of distant stars. By studying these vortices in detail, researchers can refine the broader theoretical frameworks governing magnetohydrodynamics, the science of magnetic fields interacting with plasma. Another intriguing area of study is the impact of these vortices on the Sun's periodic activities, such as the solar maximum and minimum phases. These cycles are defined by fluctuating sunspot numbers and magnetic activity, but the polar regions have always been a somewhat mysterious player in this dynamic. Polar vortices might serve as stabilizing or destabilizing forces during the transition between phases, influencing the intensity and duration of solar phenomena. The connection between polar vortices and long-term solar variability could also have implications for Earth's climate. While the relationship between solar activity and terrestrial weather remains a contentious topic, understanding the Sun's polar dynamics might uncover subtle but critical links. Variations in the intensity or frequency of polar vortices could alter the solar wind and cosmic ray influx, which have downstream effects on Earth's upper atmosphere and climate systems. As researchers delve deeper, they are also questioning the interaction of polar vortices with helioseismic waves, oscillations traveling through the Sun's interior. These waves provide vital clues about the Sun's inner structure, and polar vortices might act as focal points or disruptors of wave propagation. By analyzing this interaction, scientists could refine their models of the Sun's core to corona connectivity. The potential relationship between polar vortices and the Sun's elemental composition is another exciting frontier. Variations in plasma density and magnetic fields near the poles could selectively influence the abundance and behavior of specific ions and elements in the solar atmosphere. Such findings might illuminate the chemical processes at work in the Sun and contribute to our understanding of stellar nucleosynthesis. Polar vortices could also provide a window into the mysterious phenomenon of the solar tachocline, a thin layer between the Sun's radiative and convective zones where the magnetic dynamo operates. If vortices are influenced by tachocline dynamics, they might offer a rare glimpse into the processes driving the Sun's magnetic field generation and evolution. Understanding this connection could unravel fundamental mysteries about the Sun's magnetism. The existence of these vortices may also provide key insights into the process of magnetic field entanglement and release. The Sun's magnetic field is a chaotic and constantly shifting structure, and polar vortices might represent localized regions where magnetic tension builds up and is periodically discharged. Such processes could explain certain types of solar eruptions that originate in the polar regions, distinct from equatorial phenomena. Polar vortices also offer a unique laboratory for studying the interplay of kinetic and thermal energy in an extreme environment. Unlike terrestrial vortices, which are primarily influenced by atmospheric pressure differences, solar vortices are governed by plasma flows, magnetic fields, and radiation pressure. Studying these dynamics could reveal principles applicable to plasma containment in fusion reactors and other advanced technologies on Earth. Future missions to study the Sun's poles, such as the proposed Polar Solar Orbiter, could provide a quantum leap in our understanding of these vortices. By observing the polar regions from above and below the Sun's ecliptic plane, these missions could capture high-resolution data on the morphology, speed, and lifetime of vortical structures. Combining this data with simulations could refine our ability to predict solar behavior, a crucial goal for safeguarding space-based infrastructure. In the grand scheme, the study of swirling polar vortices is not just about understanding the Sun. It reflects humanity's deep curiosity and ingenuity in exploring phenomena that are at once distant and intimately connected to our daily lives. These vortices, enigmatic and powerful, serve as a reminder of the complexities of our universe and the infinite questions waiting to be answered. Each discovery about the Sun's poles brings us closer to unveiling the secrets of our star and the forces that govern it, while inspiring new generations of scientists to continue the journey.